All right, so today in 5.9, we're going to be looking at things that are called proportions. And you can kind of see what they're going to look like. Looks like two fractions with an equal sign between them, two ratios that are equal to each other. So a proportion is a statement that two ratios are equal. So that's what we're looking at here. And the main property that we're going to be using is called the means and extremes property. So if A over B equals C over D, which basically means if you have a proportion, then take a look at this. A times D equals B times C. So where does that come from in this initial setup? If you look, A and D are diagonal from each other. So this property says if you multiply those two positions, they're going to equal the same result you get, or the same product you get, when you multiply these two positions. Okay, so we're going to use that property to see if this works. So for instance, we know 1/2 is equal to, say, 3/6. Right? We know that's a true statement. So let's see if this property holds true. If we multiply the diagonals, 1 times 6 should equal 2 times 3. And the order that you put these in on each individual side doesn't matter. You can say 6 times 1 or 1 times 6, or you could say 3 times 2 instead of 2 times 3. But the result is 6 equals 6. So this property is true. If these fractions or ratios are actually equal to each other, then the means and extremes property holds true. So when we have a missing value and we have a variable here that we're trying to solve for, we're going to use this property to help us find it. So for now, if it helps you to draw the little loops on each one, go ahead and draw it. So something over 12 equals, or is equivalent to, -7 over 8. So we're going to multiply these. So x times 8, which I'm just going to write as 8x, has to equal, I'll do this in a different color so we can really see it, the product of these two. So 12 times -7. Now, as you get better at these, you don't have to write out the multiplication. You could just put the answer there. So we're going to get an 8x on this side, and when we actually multiply, we're going to get -84. And so we're going to solve this equation. Divide by 8. And when we do that, we get -10.5. So we're saying that x is -10.5. And what I want to show you is that if we plug in this number, these two fractions or ratios are going to be equal to each other. And how do we test if two fractions are equal? We just divide and get the decimal and see if it's the same. So if that x was a -10.5 and I divided it by 12, I get this -0.875. So if I divide -7 by 8, I must get the same answer there. Otherwise, these are not equivalent, and that means my answer is wrong. So if I do -7 divided by 8, sure enough, same answer. So I know I've created two equivalent ratios, two equivalent fractions, okay, which makes this statement true using the means and extremes property. Okay, so what happens now when it's not just single numbers or single variables? We've got expressions down there. We're still going to follow our rules of algebra and follow this property. So the first one is going to be x times 7, which we know is 7x. That's going to equal the product of these two. Now we've got x plus 3, and we're going to times it by 3. So how do we write that? We're going to put the number that's kind of by itself on the outside, and we're going to show multiplication like this. If we knew what the x value was, we would add 3 and times by this 3 on the outside. Since we don't, we're going to use our distributive property. So we're going to do 3 times x and 3 times 3. So we're going to have 3x plus 9. And we still have 7x out here. And we're just going to solve this equation. So minus 3x on both sides. We get 4x equals 9. Divide by 4. So this cancels. So x equals 9/4. Or if you're not comfortable with leaving it as a fraction like that, 9 divided by 4 is a nice enough decimal that if you wanted to, you could just call it 2.25. Perfectly fine. All right, so let's take it up even another notch here. So we're going to multiply this times this. I'm going to put the 2 on the outside. So 2 times the quantity, 5x minus 2. That has to equal this product. I'm going to put the 8 on the outside, x minus 9. All right, so I need to solve this equation. We've spent lots of time doing equations like this earlier in the year, so we're going to distribute 10x minus 4, 8x minus 72. So I've used the distributive property to eliminate those parentheses, and now I just want to get an x by itself. So since I have an x on both sides of the equation, this is just a reminder, you want to get rid of the smaller of the two to keep everything positive. So I'm going to minus this 8x, so that goes away. So that's going to leave me a 2x minus 4 equals negative 72. And now that I have a single term with an x, I want to get everything away from it. So I'm going to start with the 4. I'm going to add 4. So that goes away. So I have 2x equals negative 68. Divide by the 2. And x equals negative 34. And again, you could check this answer. You could go back and you could plug it in. Times it by 5 minus 2. Plug it in, minus 9. And then divide your two fractions and make sure that you get the same answer on both sides. Now, you don't have to do that every single time, but if you're on a test and you want to know if your answer is right, it doesn't hurt to take a couple extra seconds to plug it in and see if it works. All right, so now let's take this another step further. How can we solve real problems using this strategy? So obviously, if this is given to you, you just cross multiply is what this is called. But where in the real world are you ever going to see this? Or even in a job, where are you going to see this? This doesn't just show up on its own. It comes from something. So if you flip it over, we're going to kind of get into that. So we're going to complete this phrase. 4 is to 6 as 3 is to blank. So let's go back to something a little easier. So they're saying like 1 is to 2, the same as 5 is to what? Well, 1 is half of 2, so then 5 is half of 10. Okay, those are equal, and if you cross multiplied, you're going to get 10, and you're going to get 10. So let's set this up. 4 is to 6, as we're going to put equals. 3 is to blank. We don't know. We're going to put x. And we're just going to use our cross multiplying to solve this now. So 4x equals 18. And then you just quickly divide by 4, and you get x equals 4.5. So the relationship of 4 to 6 is the same relationship as 3 to 4.5. And if we divided those, we would see that the ratios are equal to each other. All right, so that's a basic setup. Now let's go to some word problems. So example number 3. Survey 454 college students found, so that's your total, that 409 of them had computers at home. So if there's actually 37,409 students at the school, this was just a survey of some of the students, how many would you expect to have a computer at home if we felt that this survey was a good representation of the whole school? So now we're going to set up one of these proportions, a ratio equal to another ratio, cross multiply and solve. So when I set up my first ratio, I'm going to use these two numbers. It actually doesn't matter which one you put on top as long as you set up your second proportion to match it. But we should be in a habit of kind of putting the piece that we're specifically talking about over the total, like we were when we were doing probability. So 409 out of 454 have computers. That's going to be equal to, and now we're going to have to put this 37,409 in the right spot. So that's the total students enrolled. That's the total. And what we're looking for is how many of those students would have a computer. So before you cross multiply, you should double check and make sure things are in the right spot. I've got the people with computers on top, and I've got the totals on the bottom. They match. I'm good. Okay, so now I can go ahead and cross multiply and solve this. Multiply these, multiply these. And it doesn't matter which one you put first. So if you want to multiply this one first before you multiply this one, that's fine. So just to show that, I'm going to put this one first. 454 times x gives me this. And when I multiply these two numbers together, 409 times 37,409, I've got the number right here. It looks like this. You don't need the commas. Divide by 454. Let the calculator handle the big numbers. And when we divide those two, let's see what we get. So 15, 300, 281 divided by 454. Now you'll see this is not a perfect number, right? Rarely are these going to be perfect numbers unless the 454 fits perfectly into this number and you're expanding it by a product of, say, 5 times or 6 times. If it's exactly 10 times the number, then we're going to get a nice one. But if it's not, which in real life it hardly ever is, exactly 5 times this or 20 times this, it's going to be a decimal times this, then when we kind of project out, we're going to get something that's not exactly perfect. So in this case, though, you can see with the 0 following the decimal, we can say that confidently this would project out to about 33,701. Now, does this make sense? We always should go back and see, does this make sense? So this is the students with computers. Let's say you typed some things in your calculator wrong and you just put the decimal in the wrong place, and somehow this came out to 337 and you rounded everything up. And you said there was 337 students with computers. If you think about the original two numbers and how they compare, the total students was 454 in the survey. The number of students with computers was 409. Those are relatively close numbers. You could say most of these 454 students had computers. So this relationship over here needs to still be the same. So if you look at these two numbers, 33,000 compared to 37,000, that looks similar to this. Now, of course, you could always divide these and check, but just looking, is it reasonable? I think it is reasonable because 33,000 is fairly close to 37, just like 409 is fairly close to 454. But if I got some number here that was super small, like 300, compared to 37,000, I know something's wrong. Or if I got a number bigger than 37,000, I know something's wrong. So, of course, you could plug this in and divide and actually check and see, is it correct? Now, since we rounded it, it's not going to be perfect, but it'll be super, super close. But at least check if it's reasonable, even if you're not going to plug it back in. And make sure you don't put something here that just doesn't even make sense. All right, last one. Example number 4. So 2 candidates, we're going to call them A and B, ran in a local election. Candidate A got 450 more votes than candidate B. Their vote counts were in the ratio of 8-3. How many votes did each have? So we don't know exactly how much either one has. So we need to come up with some kind of expression to represent them. Candidate A, candidate B. So once we know what candidate B is, we know candidate A had 450 more than him. So what I'm going to do is I'm going to call candidate B X because candidate A has 450 more than him. So I'm going to call him X plus 450. Whatever B is, A is 450 more than it. So if I'm going to set those up in a comparison, okay, they tell you here their vote counts were 8-3. Now that's going to expand out. That 8-3 means only 11 people voted. Now obviously that's not what happened, but that's just the ratio. That's the simplified fraction that represents the ratio of these two candidates. So what I want to do is I want to set these up equal to this. So I'm going to set up a proportion. Now how do I know which one to put on top, which one to put on the bottom? Well, I already know I'm going to set this one up 8-3. So thinking ahead, I need the bigger value on top. If these are going to be equal to each other, I need the bigger value on top. So out of these, the bigger value is the X plus 450. So that's the one that makes sense. So when I set this up, it needs to look like this. If you happen to put the X on top, then you would actually have to flip this ratio so that the smaller goes on top. And as long as you did that, it will still work. Okay, so you actually can flip both of these, and this is still going to work because the diagonals when you multiply are going to be equal. But since this gave the ratio of 8-3, we should set it up that way instead of going 3-8. But I just want you to know that it could still work as long as you have these matched up correctly. So we've got the bigger ones on top, the smaller ones on the bottom. So now let's go ahead and cross multiply. So we're going to do this. We're going to do this. So 3 times x plus 450 has to equal 8 times x. So let's go ahead and distribute. 3x plus, when I multiply these, I get 1350. All right, I have used the distributive property to simplify, get rid of parentheses. Now I've got an x on both sides of my equation. The traditional way to go about this now is to eliminate the smaller of the two, which is going to work out just fine here. So I'm going to have a 5x on this side, 1350 still left on this side, divide by 5. And let's see if this is a nice number. So 1350 divided by 5. We get a nice even 270. So x equals 270. Now, it's very easy to just stop there and move on, or just go check the answer key at this point. But let's make sure we answer the question. We haven't yet. It says, how many votes did each get? So candidate B is represented by X. So B has 270 votes. Candidate A has 270 plus 450. So we need to go ahead and we need to add that. And that means that A had 720 votes. So here's an example of how we can set up a proportion and cross multiply to help us solve a problem.